Hello there. This is a presentation about Kessler syndrome. I've taken a few days to create a formula for calculating the Kessler syndrome. It's a very complicated thing, first of all, but I managed to find to deduce a formula for calculating on a shell, you could say, or a fixed distance from Earth, and then I later managed to make that bigger so that it covers the third dimension of height also. And the result from my little research here is that it's already too late. There is 180% right now of what is required for a cascade to take place. So it's too late. And I'll show the evidence for that. And the good thing here about my presentation is that there is no simulation here. I'm not simulating anything. Everything is an analysis. It is an analytical solution to this problem. And I'm using data from NASA mostly. And I will leave some links below. This is a pretty long presentation, or we'll see what it becomes of this. So basically, it looks really bad when it comes to this. Okay, let's go. Kessler syndrome is complex, but when using the birthday paradox, which is a somewhat related math problem. I mean, it can be applied when it comes to satellites. I realized so. So one can understand the phenomenon by looking at a layer of the chain reaction. This is valid since satellites and debris move in orbits, just like a layer. This creates a separate altitude problem that will be handled later, and I'll handle this in this presentation. I'm just saying we begin with the layer things. So here's the birthday paradox. It looks like that, and you can see that already now. You can see that okay, it reminds of the formula that I have come up with. Let's now deduce that formula quickly. So this is how you deduce the formula, and I'll quickly explain it again. I made another video about this, but I didn't have the formula in place like this in a clear way. So the point here, you have a time orbit, and that is the time for the satellite to go one orbit. You know, it's the time for that, a single orbit. Time alive is the time that you can assume that a satellite will remain in orbit as long as it when it is disabled. So nothing is assisting the satellite to push further, but it simply falls slowly into the atmosphere of Earth. That is time alive, or TA. Impact time is important because that is a way to measure this birthday paradox, and that's strange. In this solution, we don't really care about how things collide, but still we're going to manage to have this collision work out in a good way, and I'll maybe explain that. if I'm not tired enough. But so the impact time is something that you so the below that you see impact orbit ratio, and that is you kind of take the whole orbit and see how much of the orbit is the impact, you know, and from that you get something that is the equivalence of the birthday problem, where you have one day which is the birthday, but instead of a birthday you have a collision. Okay, so you change the birthday problem into a collision problem, or the birthday paradox into the into a collision problem. And now I want to, you know, because this is just a shell, but we're going to make this into into another dimension. So we do this in a certain way here. So assume that the satellite is a cube. Okay, thanks to the new formula, having only 3 satellites of 1/3 the size of the cube is equally probable to collide as the original full size. This is because of the formula is independent of area of impact. And how do I explain that? So of course there is an area that collides, yes, but the formula is not dependent on that. It's simply dependent on the impact time, which is dependent on a single length. And so yes, taking only 3 satellites of 1/3 of the whole is equally probable to collide. But a consequence of having only 3 is that 1/3 of the satellite of the size is that the layer gets thinner. So that the layer is thinner if you have like that. To counteract this, use 9 satellites, fragments of the satellites of 1/3 the size. Okay, so the reason why we're doing like this is because we want something to be equally probable to collide, but at the same time it spreads out vertically. And what this means is that one can divide satellites into 27 cubes, and they suddenly span 3 times the original height, but they're with the same probability to collide as earlier. Okay, so you get something like a pillar. Okay, and this is actually what we want. So the reason why I'm looking at this is because a collision creates fragments, but I kind of assume that the fragments are there, and from that we can, with this thinking, the satellite can split into sizes down to 1 millimeter cubes. The reason for that, which is seen as the limit of what is dangerous. Okay, so the reason for that is that these satellites, or fragments, they move so quickly, so they become faster than a bullet. Okay, like 10 times faster than a bullet. If you fire a weapon, it's 10 times faster. So what's the minimal size for a debris to be still dangerous is what I'm doing here. And the result is that we get a really high pillar of satellite fragments with no loss in probability of collision. And this is because of the formula that is not, it's only dependent on the size, and that's it. not the area, but the formula has only the size. And from this, we're able to split the satellite into fragments already in the beginning. And yeah, using the new formula, we can find the number of satellites triggering the chain reaction. And in addition, this will implicate the required height of the pillar of the cascaded collision. When comparing to real-world data, it is now possible to evaluate how close it is to a situation of Kessler syndrome. Okay. So you just have to trust me on that right now this is all we need, and we're already at a place where we can look at data from NASA and simply plug it into the formula, and from this we can see that it's already too late. Okay, so here are the sources. You see NASA on many places, and you see these arrows that are red pointing to the right. These are I take each size of the fragment, or so the top one is wait a moment. The top one is 1 meter, and a 1 meter cube can split into a pillar that is 1,000 meters high with 1 millimeter big cubes. Okay, which is still dangerous. I mean, it's that's where it ends, kind of. Okay, so this is how I do the calculation. And in the same way, you get these other pillars from the other data. So this is just data. So you have low Earth orbit debris, 50 centimeter big, 25,000 of them. And it's just some, the red arrows just point at some extra data that I will be using. Like I'm calculating something on my own. Okay. So let's do this. So let's use this new formula to calculate how tall the pillars of cascading collisions are. And the variable here is the size, and that is 1 meter, 50 centimeters, 5 centimeters, and 5 millimeters. The constants are the velocity, time orbit, and time alive. And then we calculate this. Size 1 meter, we just do all this, and it takes some time to do this, but I tried many times, and I'm sure of these numbers here, and the result is totally worrying. We get a 554 kilometer pillar of cascaded debris, which is far beyond what is allowed. Okay, and let me show that to you. So we look at some other data, and all the links is below, and this shows that 88% of all satellites is in low Earth orbit. Okay, 88%. Then it looks like 75% of all are between 400 and 600 kilometers. You have this other source up here saying that 80% of low Earth orbit are below 600 kilometer, and you combine it with this one, the the table from this study, and you see that 66% of all satellites are between 400 and 600 kilometers. And from this, we take 66% of 554 kilometer, and you get a 359 kilometer pillar, which is 180%. You see, you take 359 divided by 200 kilometers, which is the total height of this altitude here, the altitude difference between 600 and 400 kilometers. And you get that, yeah, this is 180% of what is permitted, which means that it's too late. It's too late. It's over. And it's game over, basically. We're just waiting for everything to be destroyed in space. This is how it is right now. And my calculations here are proving that. And the thing about this is that, wait, let me go somewhere here. The thing about this is that it's very clean, all of this. It's very clean. It's not that I'm showing you a simulation here. No, I'm doing an analytical derivation, a calculation, which is in a way, this is stronger than just doing a simulation, because, yeah, I don't know even if a simulation would be accurate, to be honest. It's just so complicated, this. It's just so complicated. You need so much of that computer to keep track of million particles here and the sizes of these and how they collide. It's impossible, guys, to simulate this. But using this reasoning here with having this birthday paradox becoming this new formula of cascading, and combining it with the fact that you know that a satellite can be split into pieces which have the same probability to collide as earlier, and making that to a pillar, and just deciding to do that like that because it makes sense, it's like logical to do like this. Well, the results are worrying from doing like that. You get as I said, I'm using NASA data, and we get so let me maybe talk a bit more here. I did a video yesterday, or maybe, yeah, I think it was yesterday, saying that you only need 50 satellites of 1 meter size to create a chain reaction. And I define the chain reaction as something that is happening more often than time alive, you see. So within this time alive, you should have 1 or 2 collisions. And then from there, it just explodes and it becomes exponential. And so the idea of separating, like the idea of already separating everything into what they will become, it makes sense. And as I said, the argument for that is that it's independent of area of impact. It's just the impact time that is of importance. And also look how it's so shocking that you can have something that is 5 centimeters. Imagine that you have a 5 centimeter ball going on something big, okay? Well, now you have all of Earth, and you have these random directional balls or cubes of 5 centimeters. And imagine that you only need 141 of them to create a chain reaction within 5 years. Yeah. So that's the deadline. The deadline is this time alive. And so, yeah, it's too late. It's too late already. And these fragments, they stay. So they can stay in 10 years, 100 years, and so on. So once the destruction starts and becomes worse, you can see it's already a lot of small debris, but it can get a lot worse. You can see the proportion between them by looking at those pillars, and you see that it's still, like, even if you have 100 million particles that are 5 millimeters, the bottom case, it's just a 6 kilometer pillar. So there's still a lot left to become debris. There's still a lot left to become smaller and to become dangerous. When it becomes smaller, it becomes more dangerous naturally. This is the sign of the chain reaction. But the whole point is that I'm showing you that the fuel for doing this chain reaction is already in place, and it's in place where it is the most activity, or like there's the most traffic, there's the most traffic there, and there's the most it's as you can see here on this chart at the top left, the chart, you see it's the most. I did this evaluation at the place where it is the most satellites, and it's 180% of what is required to have a chain reaction. It's already too late. And please, you should check my calculations. You should check the logic that I have done, and get back to me what you think about that. So yeah, it is so let me show that logic again. Here is the key to what I'm doing. This is the birthday paradox, as I said. Like, I'm taking this many times, but why not? And the whole beauty in this is that you don't have to care about how anything happens. You don't have to worry about that. I'm not worrying about how things happen. It just happens. And this is the birthday paradox. It just happens. And the fact that it is independent of area, like, yeah, it's only the size, but in actuality it's 3D objects, right? There are 3 dimensions of these objects, but this formula only uses one dimension, one of these dimensions. And as I said, this opens up to do this conclusion about, we spread out this, and we call it equally probable when doing like that, and we get these pillars, these dangerous pillars, and then we realize that it's game over, basically. 544 kilometers pillar. So yeah, this is my presentation. And what should people do now? Well, I'm not someone that should... I'm just doing my presentation here where I tell you that it's game over. That's what I do. And me personally, well, I think the ISS and these space stations should be abandoned. Yes. Project Space is no longer possible, basically. And yeah, that's how I see it. And I believe that I don't know how quick this reaction is going to happen. So what I'm telling you is that you have to imagine that there is like a slow motion nuclear bomb in space, but there is no explosion. It's just a destruction of communication, right? The satellites. And this communication destruction, you can't stop it. You can't go up in space and catch something going 10 times faster than a bullet. I mean, and if you could, well, how many times can you do that? And you have to shoot up something else that catches it. So it's impossible. It's like game over here. But don't be upset about that now, but instead try to focus on, like, if you want to, I would be glad if someone could verify my findings here, and so that, yeah, it's basically necessary to verify what I did here, because you're going to waste a lot of money in space if you continue to, like, basically, we should already start going back in technology, back in time, because it's like we should already start to think that we cannot use satellites anymore. We have to stop that. And my formula is proving that by making these pillars of, yeah, as I said. Okay, so that's it, guys. That's my video. Usually I don't do this kind of videos. I just found this interesting doing this, and so yeah, that's my video about Kessler syndrome. It's game over. 180% of what is required, and see you. Bye.